Our webinar. I'm Neda Sadouri. I'm speaking from Tehran. We are honored to have today Professor Efrain Ferrer from the University of Texas at Rio Grande Valley as our guest speaker in our webinar on quark matter and relativistic hydrodynamics. Professor Ferrer receives his PhD at the Lebedev Institute in Moscow. His activities have been carried out at institutes in the USA, Russia, Spain, Italy, and Switzerland. And at present, he's a full professor in the physics departments of the University of Texas, Rio Grande Valley. He has a number of important contributions on quantum field theory in the presence of external magnetic fields. And his talk today is about the axion polariton in dense quark matter. Before starting, let me also add some words to the organization of this webinar. The length of the talk is maximum 19 minutes, plus 30 minutes of discussion. You can interrupt whenever you don't understand. To do this, please raise your virtual hand and wait until I call your name. Then turn on your microphone and ask your questions. But it's better to postpone long discussions to the end of the talk. And to keep the internet connection stable, please turn off your video cameras. So, Professor Ferrer, please start.
Okay, I want to thank Professor Sadouri for the invitation to present one of our recent works about, that is, the main thing is about the electromagnetic interaction in quark dense matter, and specifically when we are considering not an extreme density, but an intermediate density. That is the importance of that is related to astrophysics, because we know that neutron stars are going to be in a region where we cannot say that the density is extremely high. In the talk today, I will start by introducing a phase that is known as the magnetic dual chiral density wave phase, which is a phase that can be realized, as I will show you, at these intermediate densities. I will be repeating some of the things that Vivian was already presenting here like a month ago, but I think that it will be convenient for the people that were not in the first talk to understand better what I want to say, and also for the students to get more insight about what is the basis of this new phase and so on. Then I am going to go to look to the electrodynamics property and the anomalous property of this phase, already when you put the quarks in interaction with photons. Then I will go beyond the mean field approximation and consider the photon interaction in that system. And from there, to see the creation of a new particle, which is known as the axion polariton. And finally, looking for the Primakov effect, I will discuss how the polariton can influence the neutron star mass. Then let's remind you what are the main properties of neutron stars. Well, here we have the diameter, the mass, the temperature, and the magnetic fields. Something important is that any phase that we can have inside the neutron star has to be able, through the equation of state and the TOV equations, to get masses of the order of 2 solar masses. The other thing is that the temperature of neutron star, you see, can change in a big range. This 10 MeV is when they are just created, but relatively quick, the neutron star will already get a temperature that is of the order of 10 kilo electron volts, too much smaller, that is several orders smaller than the density that we have there. And then this is why in all this approach that we follow in order to study the TOV equations and the equation of state and so on, we take the limit of 0 temperature, because it's almost neglectable as compared with the density. And the other important thing is that in neutron star, we can have very large magnetic fields. In the case of magnetars, see that the magnetic field in the surface can be up to 10 to the 15 Gauss. And it is believed that the magnetic field inside the core, that is when you go to region of higher densities, will be even higher. And using the viral theorem, it has been found that it should be around 10 to the 18 Gauss. And even for quark matter, you can go a little higher. Well, the other thing is to understand where we are going to be working. Here, the QCD phase diagram, that is temperature versus density. When we are in the extreme region, that is low density but very high temperature, or low temperature and very high density, these are two very well known, because thanks to quark deconfinement, we can use perturbative approach. And we know that in this region, what the state of matter that we have is a so-called quark gluon plasma, while in this other asymptotic region is the CFL phase of color superconductivity. Now the question is, what happened when we are in the region where we expect to have in reality the phase of neutron stars? Then it will be an intermediate region. And this is where the attention now is focused, to see if we can get some insights about possible phases in that region. And we are going to be talking about one of these phases, which is an inhomogeneous condensate phase that can be realized at that density. And I will now discuss in general way why inhomogeneous phases are the one that will be expected in this intermediate phase. Well, here I am now reviewing some of the condensates that we can have in quark matter. Here is the chiral condensate that, as you know, is formed by a particle and an antiparticle with opposite spin, opposite momenta. The problem is that when we have density, then the particle will be sitting in the Fermi surface. When we increase the density, the Fermi surface will be increasing here. The energy gap between the two begins to increase, and it makes this phase not favorable from the energy point of view. On the other side, if we come now from the asymptotic high density region to the intermediate one, well, in the asymptotic one, as I was telling you, we have the Cooper pairing of the CFL. There, the pair is formed by two particles with opposite spin, opposite momenta. That is a constant condensate. And the thing is that when we begin to decrease the density, then the role of the mass of the S quark begins to play, which is the biggest mass of the three quarks that are participating in the Cooper pairing in the CFL, begins already to be significant. It creates a mismatch between the Fermi surface of different flavors. And then you know that it creates instability known as the chromomagnetic instability, making this phase also non-favorable from the energy point of view. And one of the possible solutions is that it is transferred to an inhomogeneous also superconducting phase. Well, finally here we have the kind of pairing that we are going to consider. This is formed by a particle and a hole with opposite spin, but with momenta pointing in the same direction. Then it gives rise to an inhomogeneous condensate. Both particles are close to the Fermi surface. Then we don't have the problem that we have with the chiral condensate. On the other hand, it's a pair formed by the particle of the same flavor. Then we also don't have problem with the mismatch. We can show that it is favored over homogeneous chiral condensate at also large magnetic fields, and it is favored over color superconductivity at large ANC limit. Then, basing on that, I will study a phase that is an inhomogeneous phase, as I told you, that is called the NDCDW phase, and I want to go over the main characteristic of this phase. Well, here you have an Ambujo-Nalassinian model already enriched with electromagnetic interaction. Here is the Maxwell term. Here is the interaction with any electromagnetic field that you can have in the system. This is the barium chemical potential, and this is the point-like interaction typical of the Ambujo-Nalassinian. Then this is the ansat for the condensate. We are going to have, you see, a condensate that is modulated by this momenta. It was proved, I think that by Frolov and collaborators, that in the case of a magnetic field that is pointing in the Z direction, that is the particular direction that we are going to specialize here, the more favored solution is the one where the modulation is in the direction of the magnetic field here in the Z direction. When we then use this ansat and go to use it in the Howard-Stratanovich transformation, we can get the mean field approximation Lagrangian, where you see the mass of the quarks becomes complex. This is a problem from the point of view of calculations, but we can get rid of the problem by making this kind of chiral Locant transformation in the quarks. And then when we do that, we end up, you see, with a Lagrangian, an effective Lagrangian, where the mass recover the way that is normally used, a constant mass, and the price we have to pay is that you see the covariant derivative now depends on gamma 5, gamma 3, and also on the isospin metrics, and other characteristics that we are going to be discussing in a moment. One of these other characteristics is this very important one, that the dispersion relation for the quarks in the lowest Landau level becomes asymmetric with respect to zero energy. That is because of this modulation term here. You have that changing here, epsilon plus and minus, you get a non-symmetric term. This is a very important property because it is known from many years already in other contexts that a spectrum that has these characteristics are topologically non-trivial, and then the system can have topological properties. The other thing is, that is the other price that we have to pay, is that when we go to the quantum theory, we can see that the Jacobian of the chiral transformation, the local chiral transformation that we were proposing is not invariant. And then we have to calculate this Jacobian. The Jacobian in this case is ill-defined, and then we have to use a well-known method that is the Fujikawa approach to regularize the theory. This is an approach that has been using in other situations that they have also singular Jacobians. And when you do that for this particular case, you can look the details in these papers. Then you end up, you see, with a new term, which is an Axion term that has to be added now to your effective Lagrangian. Then the effective Lagrangian of this theory in the presence of electromagnetic field now is enriched with this Axion term, where the Axion field is proportional, you see here, to the modulation of the condensate. Then having already this effective Lagrangian, you can calculate the action, the effective action. The effective action will give rise here to an effective potential. And from this effective potential, you can check that the minimum equations for the potential give you, as I will show you in a moment, that is, I can go there now, that is give you, you see, an answer where you see that the amplitude of the condensate is almost constant of up to certain value of the chemical potential. And now here in place to jump to zero, as it was the case when you had a constant condensate, it begins to decrease. And the other important thing is that already, even from zero, that is after you have a different, whatever it is, chemical potential, you see that the condensate already becomes inhomogeneous. That is here, of course, the inhomogeneity is very, very low, but then it will be increasing already when M begins already to decrease. Then another important thing is that when we calculate this thermodynamic potential or effective potential, and you will see that you have to be careful in doing the regularization, and it will appear there is the regularization here is a delicate point, because now you see quarks with momenta that are pointing in the same direction. Then that was done by Frolov and company, and they found that there is an anomalous component in the potential given by this. And from here you see that if you take minus the derivative with respect to the baryonic chemical potential, you get an anomalous baryonic number density. That is, you can have in the condensate already a density before the mu is larger than M. If you remember, in the typical cases when we don't have this non-topological effect, we had that only we have a density of quark when mu becomes larger than M, no? Because of the Fermi sphere. And here now we have density of barium already at very low chemical potential, because they are coming from this anomalous kind of charge. And it can be checked that this is also equal to the charge that we get through the index, the Atiyah index, that is a typical topological index. That is telling us that there is a non-trivial topology in this system that is giving this anomalous effect. If we compare, for example, the effective potential here is when we take the modulation equal to 0, we are considering here a weak coupling in order to have the same result that we have in magnetic catalysis. Then no inhomogeneous condensate. This is the value here of the effective potential, and this is for the case that we have this inhomogeneous condensate. We can see that in all these cases, the inhomogeneous condensate is energetically favorable, and mainly because of the non-trivial topology that we have now in the system that is already giving this negative contribution to the effective potential.
Sorry, Efrain, somebody has a question. I think it was the question whether you have a temperature here or not.
No.
The temperature here is 0, or it is finite?
Yeah, as I told you at the beginning, because we want to see this in application for astrophysics, we are neglecting the temperature at the beginning. Of course, temperature here, we can talk that at the end if you want. Temperature here is also important because we need to know how much temperature we need to erase the condensate. But I can tell already that the condensate here is around, in this region, is around 80 MeV. And the temperature that we have in the star is kilo electron volts. Then also there is no problem with that. We have to raise the temperature beyond the one that we have in all the stars. But
Okay.
this is a very interesting question.
So may I?
Yeah.
Yeah. So actually, why I got a little bit confused, because you have this expression of potential where you have this omega t. I think if you can please go back to that expression. Yeah. So this term here, omega t, which looks like a temperature dependent term.
That's true.
So
That's true.
For these figures, you are just ignoring it, right? I mean,
Yeah. That is here, and you can see in several papers already, and you can see the explicit contribution of all these terms. The only thing is that when we go now to calculate that what is given here for the solution of the condensate, we are taking already the zero temperature limit.
mm-hmm.
Okay, then we are neglecting that.
Yeah. Thank you.
Okay, then now here we are already considering an extra term. That is, we are considering that we are applying an electric field and a magnetic field in the system. The electric field here is perpendicular to the direction of the magnetic field in such a way that it will be perpendicular to Q. And then we see that in the Maxwell equations now appear two anomalous terms, and that come from, this one, come from the anomalous contribution in the effective potential of the zero Landau level, and this comes from the action term. And this is what in the literature is known as action QED. That is when you introduce an action term in the Lagrangian, and then you see what are the modified Maxwell equation. Wilczek found in general what are the variation that you get in the Maxwell equation, and it is called the action QED equation. Then we have now these two extra terms that will have some implications in the electrodynamics of the medium. We see that this medium exhibit magnetoelectricity. That is, if we rewrite the Maxwell equation in terms of the D and H field in the medium, we see something very peculiar. If you remember, in the definition of H, will enter the magnetization, that is B minus the magnetization. Well, now the magnetization here is a function of the electric field. That is, changing the electric field, you can change the magnetic property of the system. And the same here. When, if you remember, in order to get D, you have to add here the polarization vector, and the polarization now is given by the magnetic field. Then these are anomalous effects that give rise to magnetoelectricity in this medium. And they are coming from the two non-topological effects. Now we want to go beyond the mean field approximation. For that, we need to understand what are the symmetry breaking patterns that we have in the system. And well, we start by explicitly breaking the symmetry when we put a magnetic field. Then we break the flavor symmetry, we break the rotational symmetry, as you can see here. And then we have a second symmetry breaking when we consider the condensate. This is the ansat that we are taking for the condensate. And then in that case, we are going to break the chiral symmetry, and we are going to break, because of the inhomogeneous character of the condensate, the translation. Then we have two breaking symmetries in the system that we have to take into account when we are considering the low energy effective free energy. This is a so-called Ginzburg-Landau free energy, and we expand then in the condensate and the derivative of the condensate, and that is in doing that, I repeat, you have to take into account the symmetries, and you see that because of the magnetic field appears these new terms, the new terms that have coefficients A, that is these two, are mainly coming from the symmetry broken of the magnetic field, the terms that are now here enclosed with these squares that have coefficient B are coming from the breaking of the magnetic field rotational symmetry, plus the fact that we have a non-trivial topology. Why? Well, because you will see, look into the order parameter, that is when you already plug with the order parameter and SAT that we have for the MDCDW phase, the free energy becomes this one here, and you see that in the B terms we have odd terms in the Q field, and these odd terms can only come from the zero Landau level contribution to the effective potential. Then this is the Ginzburg-Landau free energy. This coefficient has to be found taking the derivative of the effective potential that we already calculate, and they are going to be a function in general of the baryonic chemical potential, the magnetic field, and temperature, if you want to look to the phase transition at final temperature in this system. Then we can go there, take you see the minimum equation for M and Q, and if you do that, you are going to also to find the same solution that I was showing you a moment ago that were found from the whole effective potential. Then we now have to take into account that the symmetry is reduced after the condensate to this direct product of groups. In doing that, we had two breakings. You remember the chiral rotation and the space translation. And then associated to these two breakings, we can have two Goldstone, a pion, and a phonon. And if we take now the chiral transformation of the condensate, of the order parameter of the condensate, no? And we do that, this is the chiral rotation, this is the phonon translation, then we end up for the ANSAT that we are using with this result, from where we can see that the chiral rotation and the translation are locked. Then really we have only one legitimate Goldstone, that it can be the pion, it can be the phonon, or a linear combination of them, and I will select the phonon. Then I will now make for the order parameter a series in terms of the fluctuation of the phonon, of the condensate, which is the phonon, and this is what we are obtaining. The not here means that we are plugging in the minimum solution, and then we can go with this expansion up to second order to the Ginzburg-Landau free energy. When we do that, then we end up with a low energy Lagrangian for the phonon field that is now written in this way in order to have the dimension of a scalar field. And the Vz and V perpendicular square are the square of the velocities, the group velocities of the phonon in the medium. And they are function, you see, of the parameters and the condensate values, no, Q and N, that we have in the system. Then we have already this new Lagrangian, and now we can look again to the Axion electrodynamic equation, but in a situation where we are now considering the contribution of the Axion field, that it is now, you see, taking not in the mean field approximation, but already as a field that can propagate. When you do that, and when you consider and apply electric field now in the direction of the magnetic field, and also that we have a medium that should be neutral in order to be applied to neutron stars, we end up, you see, with a couple of equations. These are the wave equations that you have for the electric field and for the phonon field, and you can see that they are now mixed. That is, in the equation for the electric field, you have a contribution coming from the phonon, and in the wave equation for the phonon, you have a contribution coming from the electric field. Then from there, I can now diagonalize the theory. That is, we are going to look for the eigen modes, that is, what are the eigenvalues for the energy in the system. And then when we do that, we obtain, you see, two eigenvalues. One eigenvalue that when you take into account this result, it can be seen that the mass is equal to 0. And this other one where the mass is already different from 0 and given by this expression. And then we say that the real eigenmodes that we have in the system is a rotated photon that is massless, and a new mode that is the one that we call the Axion Polariton. We are given this name because a very similar effect is already known in non-trivial topological insulators, that is specifically in wild semi-metals, and they found the same effect that was called an Axion Polariton in the system. Another important point in all this analysis is that when this is a very well-known result, that when you have a singular modulated condensate, it suffers from the Landau-Pierce instability. That is, when you take the fluctuations of the condensate at any given temperature, that is, the temperature can be very low, already the fluctuations of the condensate are so huge that they can erase, they can wash out the condensate. Then for that, you see, what you need is to see what are the fluctuation of the condensate. The fluctuation of the condensate at the end will be given by are proportional to the square of the fluctuation of the phonon field. And then you need to find out what is the expectation value of this fluctuation. And this is what is done here. And in the case where we don't have a magnetic field, when we use the minimum equations for the condensate in the mean field value, then you can see that the transverse mode is 0. This coefficient is identical, equal to 0. When this coefficient is 0 and you then calculate this is the result. Then you see that if you have a temperature below, this calculus is for very low temperature, you see that when you take the infinite limit here for the infrared length, then it becomes already infinite. And then if it is infinite, then you see that the condensate is erased. But the interesting thing is that when you put a magnetic field, then this coefficient becomes different from 0. This is the main effect that the magnetic field makes in the system, because we don't need in the system a critical value of the magnetic field to produce the condensate. In that sense, is similar to the magnetic catalysis case, if you remember, that the only thing that you need there was low energy, and then if you have a magnetic field, you can create a condensate. Well, here is the same, but here the magnetic field has a second important effect, that is that it prevents the big fluctuations. Of course, if you increase the temperature, then you can erase the condensate, and this is a different thing. But the Landau-Pierce instability is for any given value of the temperature. Then the magnetic field here has this important effect. Well, that was the calculation for the eigenvalues of the energy in the system. If you calculate the eigen vectors that you can have in the system, this is the one for the Axion Polariton, this is the one for the rotated photon. And now we are going to consider here an effect that is known from many, many years ago, that was found in 1951, which is the Primakov effect. That is that if you have this kind of vertex where you have anomalous contributions, you say you will have a vertex that link two photons with the phonon. And then if you take one of the photons as and apply external magnetic field, then what you have here is the conversion of the photon in a phonon. And this phonon in that medium cannot propagate itself because it is not an eigen mode, but it will propagate through this rotated photon and the action polariton. Then at the end, what we are going to have is that if a photon penetrates the medium, and once the photon already is touching the medium, it becomes an action polariton and a rotated photon. Then we want to see how it can be applied to a problem that we have in astrophysics. The problem is called as the missing pulsar problem in the galactic center. And the thing is that it is expected that close to the galactic center, the density of pulsars of neutron stars should be large. And up to now, it haven't been found. And they are now very confident that if they were there, they had to be already found because they have the technique to do it. They have found, for example, one magnetar in the region. And if they were able to find the magnetar with the technique that they are using, they are confident that they will be able also to find out other pulsars if they exist in the medium. Then there is a mystery. The mystery have been explained by different propositions. One of them is through dark matter, that if dark matter penetrates the star, then they can increase the mass and the star can collapse. And we are looking here for a different way. And the way is that if we have the star under a bombarding, you see, of gamma rays, if these gamma rays can be transformed or convert to polaritons with a mass that is already, that is for the values of mu and b that we are using, is calculated to be around 90 mega electron volts, then in that case, we can produce also a collapse. How? Well, let's review how it is done. That is, you know that there is a limit of the number of particles that you can trap in a star. This is called the Chandrasekhar limit. Then for the case of bosons, it has been done for fermions, for bosons. Then for bosons, the important thing is the ratio between the Planck mass and the mass of the particles. And it can be transferred to these values when you take into account the Planck mass. And you can see that you need a huge number. That is, the order will be really huge. Here will be of the order of 10 to 49 particles, you know, of this mass in order to produce the collapse of the neutron star in a black hole. Well, if we consider the energy output that is given by one of these gamma ray bursts that are common in that region, this is a very active region, then we see that the energy is of the order of 10 to the 56 mega electron volts of photons that are on this range of energies. Then from there, we see that in one of these events, we can produce 10 to the 59 gamma rays of larger, because here I took the upper limit, you see 1 MeV. Then if only 10 to the -4% of the photon can reach the quarks in the quark phase in the star, we are going to produce a collapse. Now the problem is, can we reach with these gamma rays the phase where we have the quarks in a neutron star? Well, for that, we need to consider the attenuation of the rays. You know that the gamma rays, when they enter a dense medium, they will decay, the intensity will decay. And depending on the density, the energy, and so on, you can find out how will be the decay from the initial value I naught to the final value I. For that, we have this formula where this sigma is the cross-section. The cross-section, of course, depends on the energy. We have the density of particles that we have in the medium, and we have the length of the medium that we want to cross. The main contribution to this decay is coming from electrons, because electrons are lighter particles. And we can have, you see, as you well know, the interaction of the photon and the electrons given by these three effects: the photoelectric effect, the quantum effect, and the pair creation. In the case of stars, the main effect is the quantum effect, because and for gamma rays of the order that we are considering. Because for pair creation, you need an energy, that is larger to twice the mass of the electron. For the photoelectric effect, you need tie electrons to the nucleus, and in the neutron stars, what you have are already nuclei or neutrons and protons, depending on the region that you are considering. And so we end up having the quantum effect as the most effective way to attenuate the gamma rays. And in order to calculate that, even we can take an approximation that is known as the Thomson scattering approximation, that is valid when the energy of the gamma ray is in this range. Then the Thomson scattering cross-section is given by this value. You see, this is a very small quantity, but the density in this medium can be large. And then we have to consider the different models that we can have for quark stars. I am calling quark stars those stars where we have quark. It can be in the inner core, as it is proposed for the hybrid case, or it can be in the whole star, as it is proposed in the strange star case. Then this is what we have. We see that the characteristic of each one of these regions, the cross, the outer core and the inner core, are different. But if we come with a gamma ray, we have, you see, to cross all these regions to touch, you see, the quark phase. And this region here, that is, if we only look, for example, to the outer core, is around 9 kilometers. It's a huge region. What do we have there? Well, there we can have mainly protons, neutrons, electrons to balance the protons, and we can have other baryons, but the number of electrons is mainly given by the number of protons that you have in the medium. Then the neutron fraction, that is electron to neutron fraction, is 1 to 8. Then what we have to see is now to calculate what is the length that we can cover without losing too much intensity. Because if we lose too much intensity, then the Chandrasekhar limit will be not fulfilled, having a density of electron that can be calculating from the density of neutrons divided by 8 in the star. And then this is what we are doing here. When we plot with the saturation density, the mass of the neutron, and the cross-section value given there, we see that the length that we can cover with this decay is almost nothing. It's 6 Fermis, 13 Fermis, and so on. Then no way in a star like this to produce the effect that we are proposing. That is to have enough polaritons inside the inner core to produce the collapse. But let's see for the other situation. That is, we know that, and this is now even a model that is the strange star model, which is the following: that is, you have a star. Suppose that you have a star like the one that I was showing you. Once the density is high enough in the center of the star to produce already a nugget of quark matter, then it is expected that the nugget will be increasing up to the moment that it will produce the whole decay of the nuclear matter that you have in the star to become a strange matter. And Wilczek was proving many years ago, and other people, but I think that Wilczek was the first one, that this strange matter is the absolute stable matter that you can have, that the energy per baryon that you have for a strange matter is even lower than the one that you have for iron. And then you can produce, you see this, we can say like a second phase transition in the star, where the whole star becomes a star formed by UDS and electrons. The electrons mainly you see in the outer part of the star, that is, the density of electron will be decreasing from the surface to the center, because the electrons are needed to balance neutrality because of the mass of the S quark. When the density is not too high, then the role of the mass of the S quark is playing a larger role in the distribution at zero temperature, and then you need to balance this, that you will have less S quarks, and then you need electrons to balance to make the neutrality, the electric charge. And when you go to the inner core, then you can neglect the MS, the mass of the strange quark, and then you will have very low electron numbers. The phase, this change in phase that is produced if you really have this strange star matter is now used to explain why you have the long delay in some gamma ray burst. That is, this is now a popular model to explain why, when you have the supernova collapse, you can see the gamma ray burst. But then after some time, a month, even more, you can see another burst, and from where this burst can come. And then they are proposing, there are already several works that are proposing that it comes from this second phase transition, when the nugget in the center becomes already, that is, make a phase transition to the whole star. And then at that moment you have another burst. Well, if you have that was also calculated, that the electrons can go even a little farther than the quark surface of the star. Why? Well, because the electrons are trapped by the electromagnetic forces that are weaker than the strong forces. And then the calculated thickness here was of several hundreds of Fermis. Then this is now the second situation that we have. That is, if the stars in the galactic center are given by strange stars, then we are going to have a gamma ray coming here. The only thing that we need is that the gamma ray will cross this thickness here of electrons, taking into account once again the decay of the electrons, the density of electrons in in this region, and even close here inside the star, were already calculated given by this expression, where this Z is the high above the quark surface. And I repeat, it is of several hundreds of Fermis. I am going to consider 100 only because that is to multiply here by 4 or 5 or so on, doesn't make any difference. That's the order. And I will also consider what will be the decay of the intensity when it is crossing this thickness. And when you do that, you see that really the density of electron there is not high enough to make a big decaying effect, that we almost get all the gamma rays in the surface already where we have the quarks. And once they come here, they try to transform in phonons, but the phonon decay or move in these two other modes that are the rotated photon and the polariton. And then the polariton will be trapped there and begins to increase the star mass if we have enough radiation coming to the star. And this is another peculiarity of these gamma ray bursts, that they go like jets, that is very narrow beams of gamma rays. If they can enter, then they will collapse the star. And that's the hope, that it could be the mechanism. Like we need that the stars there are really strange stars, and the phase of this quark matter will be the MDCDW phase, and then we will produce or explain the missing of these pulsars. Well, here you have, for example, how the mass radio of the stars behave when we have a MCDW phase. See that if we don't have, that is, if we don't put any back constant, and if we don't put any vector interaction, we cannot go up to 2. But this is typical of almost all these hybrid, that is all the stars that have quarks, that in order to go up to 2 solar masses, we have to put another interaction in the Nambu-Jonas-Arrhenius Lagrangian, that it comes from the vector interaction. And then increasing the vector interaction, then we are able here to go there. But if this other mechanism exists, then even if we don't get, the whole jet, perhaps it will help also to increase the mass of the star. Well, with that, I finish. I go to the summary. That is the main thing that we have found here is the anomalous effect that we have in the electromagnetism in the NDCW phase, that we have that and a photon there will be transformed into new eigen modes that are a rotated photon and an Axion polariton. And that once we can have this mechanism, that we can create a massive particle from gamma rays, we can, as I was just explaining, increase the mass of strange stars. Now, an outlook is that where we are considering here one of the possible inhomogeneous phases, there are other phases. There is, for example, quarkionic. There are color superconducting phases. And a very important question will be to determine what will be the more stable phase that we can have at intermediate densities. Then thank you for your attention, and that's all.
So thank you very much for this nice talk. It was very nice and very informative. I've learned at least a lot. I think there are several questions by Professor Ramezani here. I think He's also from Texas.
I see. Okay.
Yeah. You may like to ask your questions by yourself.
I know him very well.
Yeah.
Hi, friend. Hi, everybody. I think Vivian answered more or less all the questions that I put in the chat box. Vivian kindly replied to almost all the questions that I had. I think everybody sees the answers more or less. But maybe I have one more question, Efrain.
Perfect.
So in these systems, my understanding that these systems, they are highly dense systems. And I was hoping that you can see the nonlinear effect, for example, I don't know, nonlinear polaritons in this system where we usually don't have them in the solid state systems.
It could be. That's an interesting question. You mean because of the high density, no?
Yes, yes, exactly.
This is true. Because, for example, I know that because that was the first work that I did when I started my master, really. That was to see for the splitting, you see the nonlinear effects in QED when you have density. And then you have different polarizations and so on. That you have like selection rules for the polarization of the different photons and so on. And then here you can also look at that. But you see, once you penetrate that is for other situation, I don't know, because we need these high densities. These are going to be only observable in neutron stars, that is in objects like that. And once in the mechanism that I was explaining, even when you already penetrate the medium, the rotated photon that you will be looking there will be no traveling for two. I think we have to calculate that because now the density of electron is decreasing. Well, perhaps you can have it, yeah. Then there you can produce these nonlinear effects. Now the question will be, in what sense, we can use that effect to see for something else there.
Right, and actually this decreasing of the intensity of the electrons as you are going toward the core.
Yeah, you're right.
We might have also at the interface this plasma polariton wave, which are traveling on the interface. Now, this I don't think that it violates the two modes I was saying in the chat box to Vivian, that they might not violate the two modes that you have because they are traveling on the interface. They don't penetrate to the star, they don't escape from the star, they are only traveling on the surface.
Yeah, well, no, the problem is that first you have to cross, you see that that screen of electrons. That is, you can be killed there. Like your gamma ray, if the density was very large, see what happened in the outer core of a regular neutron star. The density of electron there is so high that immediately the intensity of the gamma rays coming will be decreased.
Yes, yes.
Will be killed. Now, in the case of the new star, of the strange star, the density is not so high. Then you can cross that, and then your gamma ray with the same almost intensity that had in vacuum will enter in the nuclear phase, in the quark phase, excuse me, where you only have UD and S. But when they already touch that phase, already it becomes a phonon. That is not already a gamma ray, it will be a phonon. But this phonon is not a real eigen mode to propagate in the phase. Then it immediately split in two eigen modes. This is something, for example, that was also known in color superconductivity, that the real photon in that medium, in the color superconducting medium, have to decay in a rotated gluon and a rotated photon. Well, here is a mechanism similar. And then you have that the one of these mode is a massive mode that will be trapped in the star. And that's what is important for this effect. Now what you're telling is, and what happened with the other mode, with the rotated photon? Can it have a nonlinear effects there? And I think that yes, because the density, at least the highest density, is the one that you have close to the surface. And we already were checking that it cannot attenuate completely the gamma ray. Then you can have this nonlinear effect. Now the question is, and for what this nonlinear effect will be important in the star? That's something that I don't know. I have to look at that.
Very good. Thanks, Efrain.
You're welcome.
Okay, I think Igor Shovkovi has a question. Yes.
Yeah. Hi, again. I have two short questions, actually, mostly to understand a little bit better the physics and the derivation. Regarding the physics, the first question that I have is related to the fact, what exactly is the mechanism of the collapse of the star when the gamma photons convert into polaritons? What is actually then making the star to collapse? And the technical question is about the interaction, the strength of the interaction, the coupling between these phonons due to the inhomogeneous phase and the photons, which seem to be a very strong coupling, similar to the Axion coupling, which of course is a different model. It's not the Axion, it's an effective Axion field due to this strange phase. So wouldn't the interaction be strongly suppressed between these phonons and the electromagnetic field, considering that the speed of the modes are very different and everything like that?
Well, I think that the first thing that we have to understand is that it is an anomalous effect. Okay? That is, it is not coming from any expansion that you are doing in the coupling constant or whatever. Okay, then it's an anomalous effect that you have something that is behaving as a coupling constant, but it's not the coupling constant that you have in the field. The second thing is that I think that the only thing that matters is the conservation of energy in that sort of vertex. That you need to have a gamma ray with enough energy to produce the polariton. Then if you have that, once you touch, that is, once you enter in the medium, then the polariton will be present. But the polariton will not have, that is, most of the energy is coming to its mass. But that's what you need in order to produce the collapse. Because this is what is increasing, you see, the mass of the star. Mm-hmm. But you cannot see that as a coupling that is coming from the initial theory. It is a totally anomalous effect. That whatever is,
you still need a critical amount of them before you increase the mass of a macroscopic large object by a substantial amount. So that's exactly what about this collapse I don't understand. You need some sort of like equation of state and Tov equation solution in order to say, oh, we reached that number.
Well,
don't you need that?
No. What it is used is very similar to what the people in dark matter are doing. That what they are looking is how much mass you can get inside. That's the point. If you have enough mass to reproduce the critical value of the Chandrasekhar limit, that's it. You produce the collapse. And of course, the Chandrasekhar limit comes from an analysis that you did between the gravitational pull and the...
I see the logic that you are saying now, but the difference seemed to be that when they are talking about this dark matter, they are probably assuming that it's essentially distributed more or less evenly over the whole star. And then, of course, you could use this argument. Here you are in this region of 10 kilometers, you reach the Chandrasekhar mass, and of course, there is no need to solve TOV equation. But when you are considering essentially something entering locally and maybe not even going through the whole depth, don't you need to consider sort of local, some kind of considerations rather than global?
No, I will explain you how it works, because it's similar. It's totally similar to what is happening in the case of dark matter. That is, the dark matter was entering, and the same here for in the surface. But these are massive objects. Then they begin to be attracted to the center of the star. And then you begin to create, using the center of the star, like a small dark matter star, up to the moment that already for this big nugget that you have there, you have the critical mass. Even they are neglecting the initial mass of the star, because if they get there, like a black hole, a mini black hole, it will swallow the whole star. But you don't need to do that really. You need to see that all these polaritons are going to be attracted to the center, and you begin to create a density distribution from the center to the surface, that when the mass already go beyond the Chandrasekhar limit, it collapses, because you don't have any force to sustain, the gravitational attraction. That's the same idea that people from dark matter are using. The only problem with the dark matter is that they have to explain the big gradient that you are going to have of dark matter from the galactic center to the places where you can see other neutron stars that they exist. You need to have a big gradient in order not to produce the collapse of this other. And this is an open question. People are proposing different mechanisms and things like that. But of course, in order for this to solve the pulsar missing problem, you need to have these strange stars in that region. This is something that now people are considering more and more because of this problem with the delay in the gamma ray burst. But all these are up to now hypotheses.
Okay.
Okay, thank you. There is another question by Animul, Islam.
Yeah.
So
Can
please.
you hear me?
Yeah.
Yeah. So I have a very small question from the last slide where you discussed the importance of considering the vector interaction to raise the neutron mass up to 2 solar mass. Yeah. So I have this query. We also know that for high density matter, considering the vector interaction is important because it directly couples to the this density. So my question is that do we have any estimation, whether from lattice or some phenomenological idea, which will tell me some value of this GV? Because we know that a sufficient value of GV can even eradicate the critical endpoint altogether from the phase diagram. So do we have any estimation, any idea what sort of value it can have? It can be either from some lattice study or can be from some phenomenological.
I can talk about that here. That is, lattice here cannot be used, because of the sign problem, and we are working at finite density. The only thing is that there is no clue, from where this GV is coming. This is something that is up to now put by hand. But the problem is that this GV also enters in other context of nuclear physics, for example. And then there are already several examples where if you consider a relatively high, well, you see here, this value, for example, of GV, then you are in trouble with these other situations. Then in that way, they are limiting the value of the GV. that is trying to see different implications of the value of GV for nuclear physics and this and that. And then from there, I know, and you can, that is, I have several references. If you look in my papers to one that is about gluons in EOS, that is that they mentioned the effect of gluon in this EOS for quark matter, then there are several references of this kind of problems that they were finding, that they cannot use a very high GV, because using the high GV produce collateral effects that are not good in these other situations. This is the only thing that I have seen about how to limit the value of GV. And of course,
okay.
you need here a large value, because GV, if you look to the equation, is playing a similar role to the baryonic chemical potential. It's like to increase the baryonic chemical potential. Then you have more baryonic chemical potential, you can have more masses, because you have more Fermi pressure, you know.
Okay. So this highest value that you have considered here, this GV by GS equals to 0.05, it comes within that range you are referring?
I think that that range was still, but look to that paper, to the reference.
Okay. So what is the value of GS that you have used here? I mean,
the value of
the GS.
GS is the normal Nambu-Lacinius constant for the normal interaction. I don't remember now the value, but the importance.
Okay, I can check that. Okay.
Yeah, but it's a normal value for the contact interaction in the Nambu-Lacinius model.
Yeah. Okay. Thanks.
Well,
Okay, any other questions? Comments? Any other question? Okay, if not, I have by myself a question. So a naive question. So in the first part of your talk, you have spoken about the phase diagram of this strange phase MDCW, I don't know. Yeah.
The QCD.
And you had actually two different kind of order parameters. You have M and B, and those.
You mean mu?
Yeah, you have your condensate, and also you have your the B.
Okay.
And both.
In the formulas for the MDCDW. Go to the formulas.
Yeah.
Yes.
Perfect. Yeah.
And also to the phase diagram, to the work by Frolov and also by yourself.
I see. This one.
Yes, here.
Yeah.
You have these two kind of order parameter, and both are determined by minimizing the effective potential, I think,
Yes.
which you had. And for the first one, the M, I understand that that is actually a particle, so it comes from the Nambu-Lacinius model kind of your Lagrangian. But what is actually the B? Why do you take this B as a dynamical parameter, and why do you think that it is an order parameter? I don't understand this.
Because look at this. When you have the homogeneous case, you don't have this cosine, you see? You have only M. But now you are telling that your condensate is, you see, changing in X. And the change in X is modulated by this parameter, Q. You are taking specifically Q only in one direction, but this Q becomes a new parameter here. You have two parameters that you don't know the value of those, and you have to find it through the minimum equation for the effective potential. Then now M and Q are two parameters that are unknown from the beginning. You are proposing that there is not only an amplitude of the condensate, but there is also a modulation for the, and then because you have these two, when you go to the effective potential, when you calculate the effective potential, it will be a function of Q and M. And then you have to take the derivative with respect to M equal to 0, the derivative with respect to Q equal to 0. And from there, you determine Q and M. And they are correlated. You see, for each value of M, you have a corresponding value of mu because they correspond to some given mu. You change mu, they are changing. Then here, this is going down and this is going up.
And why this kind of specific behavior? Why they are so correlated, so that the increasing B means decreasing of M?
Well,
there's an explanation behind it.
What it is telling you is that you have more density, then you have more inhomogeneity. That the density is now helping to create more inhomogeneous kind of condensate.
Neda, if I may add something, that there is a good paper that I'm going to send you the citation. For you to read. I think is Hidaka. It's a Japanese group where they did a study. They considered the Ginzburg-Landau expansion of they started with an Ambu-Jono-Lasinio, and they considered Ginzburg-Landau expansion of theory in terms of the chiral condensate. What they found is that depending on the sign of the coefficients as function of temperature, chemical potential, they didn't have magnetic field in their case. You can see that there is a region always in the chemical potential where the homogeneous condensate is not favored anymore. So you go from an homogeneous condensate, normally people go from an homogeneous condensate to a restored phase, right? That was the old assumption. What this paper shows is that that's not true. If the coefficients, they are found from the thermodynamic potential, of course, as function of the parameters, chemical potential and T. If you go to certain value of chemical potential, where before people thought the solution is restore phase, actually the coefficient changed the sign, and then that region, the only solution has to be especially inhomogeneous. What is the particular condensate is hard to tell. You have to do an ansatz. And what they do is they do several ansatz. It could be a real condensate, so like a king type of solution, or it could be a DCDW condensate, so ME to the IKX, like the one that we consider here, etc. And the only thing you could do is to compare the energies of the different ansatz and decide which one. For sure, they were favored over the restore phase, but between them, it's not clear. What happens when you put a magnetic field is that this phase, the DCDW phase, becomes the magnetic DCDW phase, and it has topological properties. So you could ask the same question, okay, is this the most favorable phase? Well, we know it's for sure more favorable than the restore one. And because it has topology is something that is robust, tends to make phase robust. So, and this phase has two parameters. You have to determine them by, you cannot assume anything. You just take the derivative and you find how they behave. You could tell that the inhomogeneous condensate is becoming more and more favored by the contribution of the the pairing between quarks and holes that happen at the Fermi surface. And this is why I mean this is hand waving what I'm saying, but it's the only explanation I can have, reasonable explanation for me, that the modulation becomes larger with increasing magnetic field. Well, I'm sorry, increasing chemical potential.
Chemical potential. Okay, thank you. Is there any other question?
Well, I have a question myself.
Yes.
But I was expecting the question, but I want to call your attention to that. We are considering a Ginzburg-Landau expansion. You remember? An expansion in the parameters M and B. And we are telling that it is a good expansion. No? M is okay. M is decreasing here in the region where we are considering the Ginzburg-Landau expansion, but Q is increasing, or B. Then how I can say that the Ginzburg-Landau was good? Well, the thing is that it happens, and not only in our system, but in other systems that have been already also analyzed, that when you look to the effective potential and you see to the coefficients in the expansion, the effective expansion that you have is in B divided by mu. That is, there is a mu that can be taken out from the coefficients, and the real expansion is B divided by mu, and B divided by mu is small. And then this is why the Ginzburg-Landau expansion here is acceptable.
I see.
So this is
very nice.
Yeah, that you can see that say, wait, why they were doing that if B is increasing and they are considering power of B and cutting the series. It's because of that.
Okay. Thank you for your question and for your answer. Okay, thank you very much. Okay, so I see a raising hand by Animal. Do you have another question?
No, I didn't have any question. I don't know why that hand is raised.
Okay, thank you. Okay, if there is no other question, let us thank again Efrain, Ferrer, and also Vivian for coming here and for speaking for us. And let us say goodbye to everybody and hope to have you again with us. I think we have, in 10 days, we have another seminar.
We had 2 more people.